The main cycloaddition reaction or pericyclic reaction that we're going to focus on is the Diels-Alder cycloaddition. And so a cycloaddition is going to be bringing two molecules together with their electrons making a ring kind of thing. So cyclo being the ring and then addition being the fact that we're bringing the two molecules together. So what we're going to be focusing on with this reaction is how many pi electrons are in each species, and pi electrons being the ones that are actually going to participate in the reaction. So we are going to have one component for the Diels-Alder cycloaddition that has 4 pi electrons, and the other component will use 2 pi electrons in the reaction. So with this first component, we have our 4 pi electrons because we have 2 double bonds. So this is going to be our 4 pi electrons, and then we have 2 pi electrons in the other component. So this is why this reaction is also known as a 4+2 cycloaddition, because we're taking 4 pi electrons and adding it to 2 pi electrons. We'll see other examples of 4+2 cycloadditions with different reactions, and we'll talk about those a little bit later. But for now, we're going to be seeing this diene and what we're going to call a dienophile as our two components. So with our cycloadditions, we saw in the previous video with pericyclic reactions, we can draw the mechanism where we're combining the two molecules. The pi bond at the bottom is going to attack the carbon of this molecule here. This pi bond is going to go make a sigma bond at the top there, and then this pi bond is going to go to make the new pi bond. So this should look very similar to what we saw in the previous video, except now we have this X group on there, and we're going to talk about why is that there. But we do need that group there for Diels-Alder reactions. Otherwise, it's too slow. So we're going to get that same type of product, just this time we have our X group, and in this case we have made our 1 new pi bond and 2 new sigma bonds, and we've made that ring. So that cyclo addition, we added these two compounds together in that ring. So the two components, very importantly, diene and dienophile for the Diels-Alder cycloaddition. So that diene is going to be that 4 pi electron component. So in this case, the diene is going to be this compound here. It will have 4 pi electrons that it uses in the reaction, and the dienophile is going to be that 2 pi electron component. Also, the diene, because it has more pi electrons for that reaction, it's the electron-rich species, and the dienophile is electron-poor. And what we're going to see for that dienophile is that this X group is going to be an electron withdrawing group, and that's going to end up making that dienophile even more electron poor, which is good for this reaction because then the electron rich component can attack it easier. We're going to talk about it in terms of just electron pushing, and we're also going to talk about this in terms of molecular orbital theory. So that's going to come back here as well because it's going to make a big difference in this Diels-Alder cycloaddition reaction. For these pericyclic reactions, in the first video, we kind of said that they're good for synthesis. This Diels-Alder reaction is very useful in synthesis and especially for constructing these 6-membered rings. So one example where this Diels-Alder reaction is used to create a molecule is tetracycline, and that's an antibiotic. And this ring that's highlighted in red here can actually be formed from a Diels-Alder reaction. So tetracycline, it has like the 4 cycles, basically, 4 rings, and that this one here in red is the one that we can actually make from the Diels-Alder reaction. So these two precursors are put together for that Diels-Alder reaction. We have, don't worry too much about these groups on the side. These are just kind of protecting groups for the different oxygens on that molecule, which we usually have to do when we're doing a reaction. But this is relatively advanced. We know we built up this molecule, and we're going to combine it with this one in order to get that ring formed. So let's see how that would look in terms of the electron pushing. So first of all, we have to identify whenever we're doing a Diels-Alder reaction, what's our diene, what's our dienophile. This is a more complex example. What we can see from just the way that these bonds are oriented like this, we have the two double bonds right next to each other. They're conjugated. That's going to be our diene component. This will be our dienophile. Here's our electron withdrawing group, and we're going to see more examples of electron withdrawing groups. This is our 2 pi electrons here, and this is going to be withdrawing the electrons from it. So 2 pi electrons, 4 pi electrons. So we have our diene here and our dienophile over here. So the diene is the one with the 4 pi electrons, and the dienophile is 2 pi electrons that participate in the reaction. So clearly this molecule does have a lot more pi electrons than just 2. We call it the 2 pi electron species just because these two are going to be the only ones participating in the reaction. And this one has more than 4 pi electrons in the total molecule, but the ones participating in the reaction, there's only going to be 4. And so when we're drawing our mechanism, we can draw the electrons flowing in that ring. It doesn't actually matter which way you start, bottom or top, because all the bonds are forming and breaking at the same time. I just decided to show it the other way this time. So this one coming down here, attacking this one to make the sigma bond, this going to make the new pi bond up here, and then this one going out to make another new sigma bond. And so if we were to highlight where all the electrons are tracing to in this reaction, let's first maybe highlight this first one up here. Those electrons from that pi bond, they're going to end up over here, making that sigma bond of the ring. And then we have our 2 pi electrons from that other component. Those are also going to be going to make a sigma bond, so that's going to be there. And then these pi electrons, they just went into making a new double bond. And so those are the new bonds that are formed in that Diels-Alder reaction. And we can, because there's no buildup of charge, it usually is a reaction you can do a little bit later in the synthesis. And so this is where an example of kind of a little bit later in that synthesis where we are able to actually make that 6-membered ring. And basically now that's left, what's left is a few oxidations in different places, removing those protecting groups, and then breaking apart this ring to make this group over here on the right, none of which we're really concerned with right now, just the Diels-Alder reaction. So that's an example of where it's used. We'll talk more about the details in terms of that diene component, the dienophile component, what do the different products, what can they look like? That's going to be the focus for this week.